Well, welcome back, everyone. We're in the home stretch. So last couple 364 assignments. Exercise sets have normally been due on Wednesday, but this last one's due on Friday. I posted it late. So get the exercise set number 9 in by Friday at noon, and exactly a week after that is when the take-home final is due. So that's Friday of finals week, again by noon. So let me just jog your memory, kind of where we were a week and a half ago when we left off. So we're in the middle of part 3 of the course. In part 3, we're asking questions like, do players reach an equilibrium of a game? If so, does it happen quickly? By which learning processes might play converge to an equilibrium of a game? And last couple weeks, we focused mostly on positive results, and positive results are really cool because they give credibility to the predictive power of an equilibrium concept. An equilibrium concept, if you want to interpret it as a prediction of how a game's actually going to be played, then you sort of feel much more confident in that prediction if you have learning processes that converge quickly to those kinds of outcomes. This week, we're going to focus more on negative results, and negative results are also important because they cast doubt, they sort of show limitations on the general predictive power of an equilibrium concept. So let me remind you, we now actually have a really kind of nice suite of positive results about computing equilibria, different kinds of equilibria, via various learning processes in different contexts. So last week we talked about regret. And so the first thing we proved is that with no assumptions on the game whatsoever, so in completely general games, no regret dynamics, so this is where each player uses a no external regret algorithm, like multiplicative weights. So if every player uses a no regret algorithm day after day to choose their mixed strategies, we showed that the time averaged history of play converges to the set of coarse correlated equilibria, so the biggest set in our equilibrium hierarchy. Okay, so no external regret gets you to coarse correlated equilibria with no assumptions at all about the games. So that's really nice. The most recent lecture, we asked, can we get that same satisfying tractability even when we zoom in? And we're more stringent about the kinds of equilibria we want. We want correlated equilibria, not coarse correlated equilibria. The answer was yes. We had to work a little bit harder. That's where we had this black box reduction that took as input no external regret algorithms, like multiplicative weights, and outputs a no swap regret algorithm. That was where we used the Markov chain trick in the analysis. So we did show that there exist no swap regret algorithms, and as a consequence, the time averaged history of play of no swap regret dynamics converges to correlated equilibria, again, quickly, in a small number of iterations. So there's also a question, and we've talked about some, and we'll talk about it more this week. Okay, so we have completely sweeping results for our outer two sets. What about the inner two sets? What about just regular old Nash equilibria, both in the mixed version where players can randomize and in the pure version where players can play deterministically? So here's what we know so far from what we've already done. The very last thing we did before we took a break was we studied mixed Nash equilibria in a special class of games, so not in general games, but in games where first of all there's only 2 players, and second of all they were zero sum. Okay, so the payoff of the row player was the negative of the payoff of a column player. It's an interesting class of games, but it's obviously not general. It's obviously special. And we showed that, again, if both players use no external regret algorithms, like multiplicative weights, then play converges to this set of mixed Nash equilibria. I've also asked you to show on the homework that if you prefer, you can also formulate any of these outer 3 problems as linear programs. Coarse correlated equilibria, zero-sum 2-player game mixed Nash equilibria. So that's a different proof of polynomiality, okay? Not by learning processes, rather by linear programming. And then the fourth one, which was now a while ago, so this was when we were talking about best response dynamics, and we were talking about potential games and specifically routing games. And we proved a result which said in a routing game where all players share the same source and the same sink, if players use epsilon best response dynamics, so as long as some player can improve by 1 plus epsilon factor, you pick some player and you let them switch. Then, under this single source, single sink assumption, epsilon best response dynamics converges to a pure equilibrium, or an epsilon approximate pure Nash equilibrium in polynomial time. So that was for this smallest set, again, not for general games, but for an interesting class, routing games with a single source and a single sink. Okay? So that's what we covered in the 2 weeks before the break. Okay, lots of positive results of when you can compute different equilibrium concepts in different classes of games. Okay? So that's where we are. Any questions about that? Before I talk about what we're going to do next? Okay. So, as usual, we have some positive results, but ideally we'd like even more. So for example, we might want to compute mixed strategy Nash equilibria beyond just two-player zero-sum games, or pure Nash equilibria beyond just single-source, single-sync routing games. So how about more, like say mixed equilibria in general two-player games, or pure equilibria, or at least epsilon approximate pure equilibria in general routing or congestion games. Meaning where different players can have different sources and sinks. That's what I mean by general. So nobody knows of a learning process that converges in polynomial time to approximate equilibria in either of these settings. Okay, there are no positive results for either of these two cases known, like the ones I've showed you for all of the other examples. So, that motivates the question, are we just lacking imagination? Have we just been stupid and there's one out there to be found? Or is there actually some kind of obstacle? Is it possible that actually there's no learning dynamics, or maybe even no polynomial time algorithm for computing these? So what I want to talk about this final week, is how you can make sense of questions like that. So how do we prove limitations on what is possible? Which is obviously an important complementary endeavor to the positive results of the last couple of weeks. So, we're familiar with this sort of issue, when you first study algorithms and you learn all these cool polynomial time algorithms like Dijkstra's algorithm and Kruskal's algorithm. You learn that minimum spanning tree is efficiently solvable, but then somehow no one ever teaches you a polynomial time traveling salesman problem algorithm. And eventually it becomes clear that nobody knows of one, and then you have to wonder if there is one or not. Okay? And we don't know the answer to that question to this day, but at least we have NP completeness, which gives us an explanation for why we haven't found a polynomial time traveling salesman problem algorithm. So what we want is the same thing here. We want some analog of NP completeness tailored for equilibrium computation, explaining why we don't have positive results in cases like this. Mixed equilibria for bimatrix games, pure equilibria for general congestion games. So we need analogs of NP completeness for equilibrium computation. So that's what we're going to do next. I want to start, so the plan is I'm going to discuss this today, pure equilibria. That's technically a little bit easier to start with. And then on Wednesday, we'll discuss mixed equilibria in bimatrix games. So most of this lecture is going to be what probably is going to seem like a digression on local search problems. So I want to talk about the complexity of local search. Just looking ahead a little bit, the connection is going to be, you can think of best response dynamics as a local search looking for a pure Nash equilibrium, or specifically for a local minima of the Rosenthal potential function. But anyways, the point is this theory was developed quite a while ago, back in the mid-'80s. And the authors, Johnson, Papadimitriou, Yannakakis, they did not have equilibrium computation in mind. They had local search problems in mind. But it turns out, and this became clear more like 10 years ago, that this is exactly the relevant complexity theory to make sense of this question. Is there a polynomial time algorithm or learning dynamics for pure equilibria in general congestion games? The answer seems to be no. It's going to suggest the answer is no, and this complexity theory will explain in what sense. Okay. So again, I'm going to connect this back to routing games in pure equilibria at the end of the lecture. But for now, it's just going to be a discussion of complexity of local search. All right. So let me just say a little bit about local search. Hopefully you've all seen it, at least in passing somewhere. A canonical example of a local search problem would be max cut. So in the max cut problem, the input is an undirected graph. Edges have weights, non-negative. feasible solutions are just the cuts. Okay, so some of the vertices S are on one side of the cut, and the other vertices S bar are on the right side of the cut. Both S and S bar should be non-empty. So in general, in a cut, you have some vertices, you have the other vertices. Some of the edges are going to have both endpoints in S. Some of the edges will have both endpoints in S bar, and then they will be crossing edges, edges with one endpoint on each side. And the goal in the max cut problem is to maximize the total weight, the sum of the weights of the crossing edges. Okay. So, unlike the minimum cut problem, this is an NP-hard problem. I mean, you could try flipping all the edge weights and computing a min cut, but actually all the min cut algorithms you learned at a polynomial time don't work for negative edge weights. Okay, so they're really different problems. Max cut is NP-hard. So, one heuristic you can use for max cut, among other problems, is local search. And people, this really is a heuristic that people use quite a bit for NP-hard problems, including for max cut. And so the heuristic is you start with some arbitrary solution, like maybe the first half of the vertices on the left, the other half on the right, just to get going. So you start with an arbitrary feasible solution. And then as long as there's a local move, and I'll explain what that means in a second, as long as there's an improving local move, a local move that makes the solution better, you just do it. Okay. And so a local move, so this is context dependent, what's a local move, but in max cut, the obvious notion of a local move is you take one vertex, say on the left side, and you move it to the other side, always making sure both sides are non-empty. Okay? So you just switch one vertex. So for example, from S to S bar. So that's a local move, and a local move is improving if, go figure, if the sum of the weights that edges crossing the cut becomes bigger, because that's what we want. So when you make a local move, how does the objective change exactly? Well, when you move it, say, from the left to the right, from S to S bar, there are some edges that didn't used to get cut, now they do. Some edges that used to, and then vice versa. So think of V as moving from S to S bar. So if V is getting moved, if U is an S and V is now an S bar, this is an edge which is now getting cut that didn't used to get cut. Okay? So if we sum this over edges still on the left, these are the newly cut edges. And then if we look at the vertices on the right, V is now joining all of those vertices. So those are edges that used to get cut and now they're not. Okay, so these are the newly uncut edges. And so if that difference is strictly positive, then moving the vertex increases the weight of the crossing edges, so that's an improving local move. Local search just says as long as you can make a move like this, make one. And local search then terminates with a cut where there are no improving local moves, and that's a locally optimal solution. Okay? All right, so one thing which maybe is obvious, but let's just be clear about. Just because you found a solution which is locally optimal, that you can't improve with a local move, does not mean, in general, that you found a solution which is globally optimal. Okay, so maybe by moving a bunch of vertices at once, you could get a strictly better cut. So let me just give you a concrete example. So note, local opt does not imply global opt. So just consider a clique on 4 vertices. With edge weights 1 through 6. So let's examine this cut here. Okay, where the left nodes are S and the right nodes are S bar. So the total weight of the crossing edges here is going to be 15, right? 1 plus 5 plus 6 plus 3. I claim this is a locally optimal solution. That means any local move only makes it worse. Okay? So a local move here is going to give me a cut with 1 vertex on one side and 3 vertices on the other side. So the cut edges are just going to be the 3 edges adjacent to a single vertex. So the possibilities are this cut, which would have weight 11, this cut, which would have weight 12, this cut, which would have weight 11, and this cut, which would have weight 8. Okay, so those are all worse than 15. So this is indeed a locally optimal solution. But it is not a globally optimal solution. That would be putting the 2 top edges, so top vertices in one side and the bottom vertices in the other. Then we cut the edges 4, 5, 6, and 2 for a total of 17. Okay? So a local search is nothing but a heuristic. It's a often very useful heuristic, but it is a heuristic. Okay? And as such, you might expect that computing merely a locally optimal solution to a problem like max cut could be easier. It's certainly at least as easy as computing a globally optimal solution, because global optimal means local optimal. And once you see this gap, you think, well, maybe it's actually strictly easier to merely compute a locally optimal solution. And that generally is true. So let me give you a very concrete example of that. So think about max cut, but let's say rather than having all of these different weights, so it's some arbitrary graph, not necessarily a clique, some arbitrary graph, and all the edge weights are, let's say, 1. Okay? So now the max cut just strives to maximize the number of cut edges. Okay? So one fact, which I hope you find easy to believe, is that the problem is still NP-hard in this case. If you really wanted to find the best solution, it's an NP-hard problem. But finding a locally optimal solution is not hard, okay, if all the weights are 1. In fact, I claim if you just run local search, this algorithm here, I claim this can't run very long. And remember, when local search terminates, it certainly terminates at a locally optimal solution. I claim that it terminates in, at most, the number of edges iterations. So do you see why that's true? So in an iteration of local search, and you make a move, what can you say about the objective function value? It goes down. Good. And if all the weights are 1, what's the minimum amount by which it will go down? Well, yeah, it goes up, excuse me. What's the minimum amount by which it will go up? It'll go up by 1 for sure, okay, because everything's integral. What's the minimum possible objective function value? 0. What's the maximum possible objective function value? Well, if it's bipartite, you can cut all the edges, okay? So the maximum number of iterations, because you improve by 1 every time, and the maximum is the number of edges, is the number of edges. So local search is just going to reach a locally optimal solution blazingly fast with unit weights. Right? So it's definitely easier than finding a globally optimal solution. Okay? And just again, so to give a forward pointer, as far as equilibrium computation, it's the local search problem that we really are going to care about, not the globally optimal problem that we're going to care about. Okay? So it's really local search we need to understand. All right. So for max cut at least for the special case where all the weights are unit, computing a locally optimal solution is easy. How do you do it? Just use local search. So here's a fact. If we drop the condition that the weights are unit, if they can be arbitrary integers, so that this maximum cut value could be very large, okay, exponentially large, say, in the size of the graph, then nobody knows how to compute a locally optimal solution, a locally maximum cut in polynomial time. Okay? No one knows how to do that. So I want to emphasize, the claim here is stronger than just asserting nobody knows if local search terminates in polynomial time. In fact, as we'll discuss later, well, it's known that local search does not terminate in polynomial time for weighted max cut. What I'm saying here is, suppose I even allow you to compute a locally optimal solution any way you want. Okay? I don't care if you use local search. Okay? Use the cleverest polynomial time algorithm you can come up with. Even with the complete range of polytime algorithms, nobody knows how to compute a locally optimal solution of max cut instances with general weights. Okay? So the plan for the rest of the lecture is I want to tell you sort of the more classic complexity theory, which formalizes the negative result here, the idea that the reason we don't have such an algorithm is because we suspect no algorithm exists. It's complete for the appropriate complexity class. And then I'll conclude by making the connection back to pure equilibria of routing and congestion games. Okay? But so the next step is, all right, we're stuck on weighted max cut. We don't know how to compute a locally optimal solution. Can we somehow prove that it's not that we're being stupid, it's that there doesn't exist any polynomial time algorithm for finding a locally optimal solution. All right, so what would that look like? Just as a theorem statement, saying that there doesn't exist a polynomial time algorithm. Well, the strongest statement obviously would just be what I just said. The unconditional result, the strongest negative result you might prove is that you just say, among all polynomial time algorithms, none of them work. So an unconditional impossibility result. Now, we don't really have any results of that form. Right, so in particular, if you could prove there was no polynomial time algorithm for finding a locally optimal max cut, that would separate P from NP. Okay? So that's a little ambitious for today, at least. Okay? So we're not going to try to prove unconditionally that there's no polynomial time algorithm for computing a locally optimal max cut instance. So the next best thing then would be, well, we know about NP completeness. We agree that NP completeness is, in some sense, the standard means that you argue that a problem in NP is intractable and seems to require brute force search or something very close to it. And it turns out NP completeness is also too strong a goal for local search problems like max cut. There's a sense in which computing locally optimal solutions really is easier than NP hard problems, and that I'll make precise on Wednesday. Okay, but for now, I just want to point out, we're not going to prove that there's no polynomial time algorithm. That's too strong. We're not going to prove that it's NP complete. That's also too strong. So instead, we're going to develop an analog of NP completeness tailored for local search algorithms, okay, as a way of arguing that we don't think a polynomial time local search algorithm for max cut exists. So here's going to be the plan. I'm going to write down right now the English interpretation of the theorems we're sort of shooting for. We're going to formulate and prove theorems that say computing a locally optimal solution of max cut is as hard as any other local search problem. Okay? So this is what we're shooting for. This is what we're shooting to formalize and prove. And again, the intent here is to have an analogy, or a sort of analogous version of NP completeness tailored for local search problems. One way to interpret NP completeness is that's a problem which is as hard as any other problem for which you can efficiently verify solutions, efficiently recognize a solution. So this is what we're going to prove instead, as hard as any other local search problem. So if max cut is sort of as hard as completely abstract, completely general local search, there's a sense in which we then don't expect there to be algorithms significantly better than local search itself. Again, remember, for these problems, I want a locally optimal solution. I don't care how you do it. If you use local search to find one, great. If you use some other clever algorithm to find me a locally optimal solution, I'm just as happy. Okay? So if we can formalize and prove this idea, an interpretation is that we don't expect to improve much over local search. In exactly the same sense as for an NP-complete problem, we don't expect to improve much over brute force search. Okay. As a bonus, it's also going to imply, once we formalize this theorem, that local search takes exponential time. Okay. So again, as far as the analogy with NP and NP completeness, you can think of problems in NP as problems where you can efficiently recognize a solution, the problems which are solvable via brute force search. NP completeness says, well, you can't do much better than brute force search. We're going to do the problems that are solvable by local search, okay, which is in some sense a little bit more structured, a little bit more guided than brute force search. And we're going to try to prove the hardest problems of that type where you can't beat local search, which is exponential time. Okay. Yeah?
By any other local search problem, you mean like any other problem about which you use the local search algorithm?
Basically. Yeah, that's the intuition, and the formal definition is coming up. So yeah, so formalizing this, we have two things to formalize. First is as hard as. This is just going to be a reduction, so most of you should have strong intuition of what this is going to look like. What we really need to be a little bit more careful about is what is a generic local search problem. Okay, so that's the next definition. Okay. And so again, keeping the analogy with the class NP in mind, so NP you can think of as the class of problems that are generically solvable by brute force search. Okay? So I don't know what definition of NP you've seen, there's a bunch of them, but one of them is they're problems that are characterized by an efficient verifier. Okay? So if I show you an alleged solution, you can quickly check whether or not it is one, like a Hamiltonian cycle in a graph. If I show you one, you're like, yeah, it's a Hamiltonian cycle. If I try to fool you, you can easily check that it's not a Hamiltonian cycle. Okay? So NP defined via efficient verifier, that's just sort of asking what is the minimal ingredients that I need to solve a problem in exponential time using brute force search. I need a verifier to tell me that when I try a particular solution, whether it's a solution or not. So here, to define very generically what is a local search problem, we need to ask what are the minimal ingredients that we need for the local search algorithm to be well defined. Starting from an arbitrary solution, keep moving to better and better solutions until at some point you get stuck and there's no improving moves. Okay, so what are the minimal ingredients we need for that algorithm to be well defined? Okay, so rather than one polynomial time algorithm, an efficient verifier, here I'm going to use three. So a generic local search problem has three polynomial time algorithms. The first one, given an instance like max cut, okay, like a graph, just tells you where to get started. It gives you an initial feasible solution. So again, it's just for max cut, maybe it's the first half of the vertices on the left, the second half of the vertices on the right. So some canonical way of getting started. So that's important for running local search. You need to have an initial feasible solution. Now in local search, you're trying to optimize something, okay, like max cut. Okay. So we want an algorithm which tells us how well we're doing. That for a feasible solution computes for us in polynomial time how the objective function value of that feasible solution. And thirdly, if we're at a solution which is not locally optimal, we need to know where to go next. Okay? So this third algorithm is just going to be like an oracle which says, oh, this isn't locally optimal, and here you should move to this neighboring solution. So given a feasible solution, either report you're done, or if not, produce a better neighboring solution. Let me just say better solution. Okay. Yeah.
I assume that there has to be a finite number of solutions.
Yeah, so by virtue of being polynomial time, it's sort of built in, right? So an instance has some length, it has some L bits. And so each of these algorithms, by being polynomial time and L, the input length, they can only operate on strings of length some polynomial in L. So that's going to then basically says it basically says everything you're operating on are bit strings of some length polynomial in L. So it's an exponential upper bound on what you might ever see. So that is a consequence of this polynomial time constraint.
Seems like you could be operating some real numbers.
That's not how it's specified. So the input's specified just as bits.
Okay.
Yeah. Good. So given 1 through 3, this is enough to run the local search algorithm. You invoke algorithm 1 to get started. You iteratively invoke algorithm number 3 to generate new solutions. You can use algorithm number 2 just to verify that you're making progress with algorithm number 3. And at some point, you'll run out of, there's a finite search space that's sort of implicit in the polynomial time definition, and eventually you'll run out. Okay, so you'll halt necessarily at a locally optimal solution. Okay. So in some sense, again, so why do we make this definition? We have this very concrete problem we care about, max cut. And we want to say it's hard. And so what we're trying to do is say it's as hard as any conceivable local search problem. So this is our attempt at any conceivable local search problem. Okay? Exactly in the same way that if you have a concrete problem like traveling salesman problem and you want to prove it's hard, the more things you can prove it's at least as hard as, the stronger the evidence of intractability. So we're making this as abstract as possible to have the strongest possible intractability instance for the problem, evidence for the problem we actually care about. Max cut for now, and then pure equilibria later. Okay. And so then the goal, given this, is just compute a locally optimal solution. Again, an algorithm which is correct would be just run local search. That's guaranteed to terminate a locally optimal solution. But for the purposes of the computational problem, compute a locally optimal solution by any means. If you have some other clever algorithm which can just zoom right to a locally optimal solution, I'm totally happy to receive it. Okay? So that's the complexity class PLS, defined by Johnson, Papadimitriou, and Yannakakis. And again, the intent was to make it as big as possible so that any complete problems for this class are as hard as possible in some sense. All right, questions about the definition of PLS? Yep.
Can you swap out the third argument with just one that reduces all the neighborhoods of the current reasonable solution?
Yeah, so the neighborhood is sort of implicit here. So there isn't an explicit neighborhood in the description. I mean, in some sense, the neighborhood is just the range of that third algorithm. So I haven't a priori defined a neighborhood. Okay. Sort of, I mean, the definition of the neighborhood is just totally implicit in what that third algorithm happens to do. Right? So if it declares some solution locally optimal, then you can conclude, it tells you something about the neighborhood. Yeah. Right. So again, just to connect this back to max cut. So in the first algorithm, again, this just returns any old cut, doesn't matter which. Second algorithm, this is clear. You just you just evaluate the weight of the crossing edges, clearly polynomial time. In the special case of max cut, the natural way to implement this third algorithm is simply to try all of the linear number of local moves and see if any of them are improving. And if one is improving, then return an arbitrary such move. If none are, you report locally optimal. Okay, so in the concrete case of max cut, that's what this algorithm looks like. Okay? But for a generic local search problem, this is all we ask of it. So computing a locally optimal solution of a max cut instance is certainly a member of PLS. And any local search problem you've probably come across in your career is probably a member of this PLS class. Okay. So, good. So PLS is our definition of any other local search problem. And that's the harder definition. And now let's just dot the I's and cross the T's for as hard as. Okay? So this will be familiar from NP completeness. So we want a notion of a PLS complete problem. A problem as hard as anything else in PLS. So we need a notion of reduction. And so a reduction from one PLS problem to another, well, so we just follow our nose with this definition. Right? We know the point of this definition is to say if we can solve L2 in polynomial time, then we can solve L1 in polynomial time. L1 reduces to L2. Okay, so we can transfer tractability or intractability in the opposite directions. So if you think about that, okay, so suppose I gave you as a black box an algorithm for L2, you want to solve L1. So what you want to do is, first of all, you want to say, okay, well, I need an instance of L2 to invoke my black box. Okay? So I need some polynomial time algorithm that takes an input to L1, makes it an input to L2. So I can feed it into the black box. And then the black box gives me an output. Okay? So it gives me a locally optimal solution for that instance of L2, which is not what I care about. I care about my old problem. So I need a second algorithm that maps that locally optimal solution to the L2 problem back to one for the L1 problem. Okay? That's it. So polynomial time algorithm A that maps instances of L1 to instances in L2. And a polynomial time algorithm B that maps solutions, meaning local optima, of the L2 instance to a local optima of the original problem I care about X. Okay. So this one just maps inputs of L1 to inputs of L2. This one maps solutions to L2 back to solutions to L1. And basically, by definition, I set up this definition so that if you give me a polynomial time algorithm for L2 and there's a reduction, I can combine those three algorithms to solve L1 in polynomial time. Okay. Yep.
What are these polynomial times?
The input. The input. Right? So an instance of a problem has some input length.
Okay.
Yeah. Okay. And then, so with the reduction, the notion of completeness is the usual one. So a language in PLS, or a problem in PLS, is PLS complete if every problem in PLS reduces to it. Okay. So all of the definitions have been concocted so that if you have a polynomial time algorithm for a PLS complete problem, that is an algorithm which finds a polynomial time a locally optimal solution, then you have a polynomial time algorithm for every PLS problem. Okay. So in that sense, these are the hardest problems in PLS. You solve one of these, you get the whole class PLS. Okay. So that should all be familiar from NP completeness. All right, where are we? There we go. So cool definition. You wonder if it's too cool to be true, in the sense that, could there really be a single local search problem, especially a problem we might actually care about, that somehow simultaneously encodes the complexity of local search just generally? And we're all a little bit spoiled because we're so used to NP completeness. At this point, we kind of know that theories like this do exist. If you'd never seen NP completeness before, this would maybe seem far-fetched. Okay, so how can you have one problem simultaneously encoding every single local search problem? But why not? We know that 3SAT or TSP or whatever simultaneously encodes all problems that you can efficiently recognize solutions. So why not have a parallel for local search? Okay? And it turns out you can. So the first such results were in this original Johnson-Papanier-Yannakakis paper. There's also a very important follow-up by Schaefer and Yannakakis, which says there exist PLS complete problems, including many natural problems that we actually care about, not just contrived complete problems. In particular, including max cut with general weights. Okay? There's lots of others as well, but for today's lecture, I'm just going to use max cut. Okay. So I'm not going to prove this fact. I mean, in some sense, at a high level, you know how results like this go. So first, you need some analog of Cook's theorem. So for NP completeness, Cook's theorem says that 3SAT at least is NP complete. So it says that it's sort of the thin end of the wedge, right? There's some problem that you might care about and seems expressive enough to encode other problems, which is indeed NP complete. Then you have an analog of, say, what Karp did a year later with lots of other problems that 3SAT reduces to, and then those become NP complete as well. So Johnson, Papanier, and Yannakakis gave an analog of Cook's theorem for a problem called circuit flip. So it's not a logic problem, it's a circuit problem, but it's the same kind of flavor. And it's sort of, the difficulty is polynomial in the difficulty of Cook's theorem. Okay, so it's a little harder, but it's not that much harder. But the analog of the initial Karp reductions, showing that lots of other natural problems are PLS complete, that was done by Schaefer and Yannakakis, including for max cut, and that's actually quite hard. Those are some of the more intricate reductions I've seen. It's a very sort of impressive work. Okay? But happily, we can just sort of stand on the shoulders of these giants and use this in our own work. That's the great thing about complete problems. Once someone proved it complete, you can just use it for your own devices. Right. Okay, so we'll assume this from here on out. All right, so there's also an interesting corollary which comes out of both of these works, which is that even in the perhaps unlikely case okay, so we don't know if P equals PLS or not. Okay? It would be very surprising if they were equal. It wouldn't be as sort of shocking as if P equals NP, but still people believe these are different. And, but even in the case where P equals PLS, a consequence of this work is that local search at least, okay, so the generic local search algorithm takes exponential time in all known PLS complete problems. Okay. So summarizing, consider a PLS complete problem, like, for example, max cut with general edge weights. The first statement is, there's no polynomial time algorithm, local search or otherwise, that's guaranteed to find a locally optimal solution unless P equals PLS. Okay? So for all we know, P equals PLS, and there is some very clever polynomial time algorithm that finds local optima, but that's the only way it can happen. As long as P and PLS are different, you cannot find a locally optimal solution efficiently by whatever means. That's statement one. Okay? So that's a conditional statement, because it's conditional on these two being different, which we don't know. The second assertion is different. It's unconditional. It says, no matter what, P equals PLS or P not equal to PLS, the specific algorithm of local search is slow, in the worst case, exponential time, for any PLS complete problem. Okay? So those are two different points, an unconditional result and a conditional result. Okay. Good. So and as far as this exponential local search time, we'll see this in action in a second. But the way it works is, first of all, you just prove for the analog of Cook's theorem, for the circuit flip PLS complete problem, you just prove directly that local search can take an exponential number of iterations. And then it turns out that's preserved in all known reductions that establish PLS completeness. Okay, so you transfer not just the PLS completeness of the source problem, but also the lower bound of exponential iterations on local search. That's why that's true. Okay. All right. So that's what I wanted to say about complexity of local search. So the rest of the lecture is about connecting this to pure equilibria.
So what we don't know is that there might exist PLS complete problems in which local search is polynomial time.
Yes, but if that's the case, it is not done by local search. It has to be done by some other kind of algorithm.
But you said local search takes exponential time in all known PLS complete problems?
Oh, right. Good point. So as far as I know, I don't believe it's known that, I don't know of any generic result which says every PLS complete problem takes exponential time with local search. I'm pretty sure that's not known. So basically, we only know it because it's true for the original problem, circuit flip, and it always gets transferred by reductions. That's my understanding of the state of the art. Good question. Okay. All right, so let's connect this back to pure equilibria. So let's understand how PLS completeness gives us an explanation of where our positive results stopped for routing and congestion gains. So this last part of the lecture I'm going to phrase in terms of congestion games. But to first order, you should just think about these as being atomic selfish routing games. I mentioned congestion games in passing a while back. And the context when I mentioned them is I said, well, we were proving all these things about atomic selfish routing. The price of anarchy is 5 halves. There's always a pure strategy Nash Equilibria, et cetera, et cetera, et cetera. We had all these cool positive results. And at one point I remarked, and also we never used the fact that it was a graph or the fact that strategies were paths. Strategies could just be any old subsets of the edges, and all the positive results would still work equally well. Okay, so congestion games are just routing games where strategies are arbitrary subsets instead of necessarily paths. Okay, it's going to be more convenient for this lecture to work with congestion games. But again, in your mind, think selfish routing games. That's totally fine. Okay. So let's just start by connecting pure equilibria and congestion games to this class PLS we just discussed. So the first claim, just to make sure we have all the definitions straight, computing a pure Nash equilibria. And so again, there can be multiple pure equilibria in these games, and I don't care which one you give me. This is going to be sort of the easiest problem about pure equilibria. If there's many, just give me one. That's all. That's your only responsibility. So computing a pure equilibrium of a congestion game, if you think of that as a computational problem, that is in PLS. Okay? So when I talk about computational problems, I mean, I should tell you how the input is described. So again, if you think about a selfish rounding game, then I just sort of give you the network. I give you this directed graph, and I need to tell you what the cost functions are. Right? So if there's k players, I need to tell you the value of a cost function at the integers 1, 2, 3, 4, all the way up to k. Okay, so I just give you those numbers as a list. Right? So I give you a graph and I give you the cost functions. For a congestion game where you don't have a network, I just give you a list of the strategies that each of the k players is allowed to use, okay? And the cost functions. So you're given a congestion game in that description, and I want any pure Nash equilibrium of it. So the first claim is just that this problem is a member of the class PLS. Okay, so it's no harder than PLS. The hardest it could be is PLS complete. Okay, it's inside PLS. So for this, you just need to remember how we proved guaranteed existence of pure equilibria in these games. And the way we proved it was using this Rosenthal potential function. Okay? So recall that the pure strategy Nash equilibria of a congestion game are exactly the local minima, where here a local move is just a single player strategic strategy. That is, local moves are unilateral deviations. Local minima of the Rosenthal potential, which was just some function. Okay, so this is a strategy profile. It says who picks which strategy. You have edges or resources. You just sum over all of the edges. And then on a given edge, what you do is you just sum up to the number of players that use that edge. And you just evaluate the cost function at the edge at 1, 2, 3, all the way up to the number of players that use it. Okay? So we saw this. This is how we proved existence. The context there is we wanted to prove there exists at least one pure Nash equilibrium. So we showed that for this function, whenever a player has a unilateral deviation, the change in phi is exactly the change in the deviating player's cost. Therefore, the global minimum was a pure Nash equilibrium. We also observed the stronger statement that actually not just the global minimum is a pure Nash equilibrium, but any local minimum of the potential function is a Nash equilibrium. And that's the if and only if. Okay? Also, best response dynamics. So what is best response dynamics? That just says, well, there's a player with a unilateral deviation who can make themselves better. Okay? But if you think about it, that's exactly the same thing as while there's a unilateral deviation that would decrease the potential function. Because again, remember, when anybody changes, the decrease in their cost is exactly the decrease in phi. So there's an improving move with respect to phi, if and only if someone has an improving unilateral deviation. So best response dynamics is nothing more than local search for the problem of minimizing phi. Okay. So this is why computing a pure Nash equilibrium of a congestion game is just a PLS problem. If you want to be more formal about it, I would have to actually specify these three algorithms. So algorithm 1 would just give an arbitrary strategy profile, like every player just picks their first strategy. Algorithm 2 just evaluates the Rosenthal potential function. And then algorithm 3 just checks for a best response by every player. Okay? So that's membership of the Nash equilibrium problem in PLS. All right? So any questions about that? All right. So this hopefully shows we're on the right track. So this is what suggests that maybe PLS is the right complexity class to reason about this problem. And so the kind of really interesting result, which is Fabricant, Papadimitriou, and Talwar about 10 years ago, is that it's not just a member of PLS, but it's PLS completes. Okay. And so this I want to prove to you assuming that max cut is PLS complete. But again, before I prove it, let me just sort of remind you what are the implications. So no polytime algorithm for computing a pure Nash equilibrium unless P equals PLS. So this is the conditional statement, and then the unconditional statement is best response dynamics in any event takes exponential iterations. Okay, so these are consequences of this theorem. Okay. All right, so any questions for the proof? And again, as far as the big picture, this is explaining why our tractability results for the pure Nash equilibrium case were limited to the symmetric case, single source, single sink, or equivalently all players having exactly the same strategy set. Okay, this is basically giving us matching negative results for congestion games, because this is going to be for asymmetric congestion games. They'll be PLS complete. Okay? All right, so proof. Well, we certainly don't want to prove completeness from scratch, right? You just want someone like, Steve Cook or like Johnson, Papadimitriou, Yannakakis to prove that kind of result once, and then you stand on their shoulders. So we want to reduce from some problem. I've only told you one problem. So, given an instance of max cut for which we want to find a locally optimal solution, I need to produce for you a congestion game so that if all we have to do is find a pure equilibrium in that congestion game, we'd be done. We can map it back to a locally optimal max cut. So we're given a graph with edge weights, and we're going to construct a congestion game. So in other words, in our reduction, our definition of reduction, we had two polynomial time algorithms, A and B. This construction is the polynomial time algorithm A. It's going to map an instance of one problem to an instance of the other problem. So the players in the congestion game will be in one-to-one correspondence with the vertices of the graph. Okay? Jumping ahead a little bit, each player is just going to have two actions, two strategies. And so that means that the strategy profiles, the 2 to the n strategy profiles, will be in a natural correspondence with the 2 to the n cut to the graph. Okay? So the edges, if you like, or the resources of this congestion game, there's going to be 2 resources for each edge of this graph. Okay? We're going to call these R sub E S and R sub E S bar. So let me tell you, this will make more sense once I tell you these strategies for each player in the congestion game. So player V has 2 strategies. Intuitively, this player picks whether it's on the left side of the cut or on the right side of the cut. Okay? But formally, it has 2 strategies. So again, we think of this player corresponds to a vertex in the given graph. Okay? if the vertex V in the given graph G, or the max cut instance, if it has, say, 7 incident edges, then in the congestion game, this player is going to have 2 strategies, each of which is a set of 7 resources. Okay, so the resources in its strategy will correspond to incident edges back in the max cut graph. Okay? So it's 2 strategies. So again, these are the incident edges to V in the max cut graph G. This is 1 resource per incident edge. One of the strategies, it's the resources with the superscript S, and then there's a sort of identical copies of it. So again, if it has 7 incident edges, this is a strategy comprising 7 resources. This is a strategy comprising 7 different resources. It has to pick one or the other. Okay. Now, notice, so think about things from a resources perspective. Okay, so I claim in this congestion game, not a lot of things can happen. Okay, so the loads on resources are highly restricted. So consider an edge of the original max cut graph with endpoints U and V. Okay? So if you think about things from a resources perspective, so some resource corresponding to some edge E, there's only 2 players of the congestion game that are in a position to use this resource. Okay, so look at a resource with it's superscripted by an edge with endpoints U and V. Only the players U and V possess strategies that include this resource. Okay, so I'm a resource. Some players can use me, some players can't use me. And when I survey the landscape, I notice there's actually only 2 players that have a strategy that would impose any load on me. Okay, and they're the players U and V, the endpoints of my edge. So my load in this congestion game in every strategy profile will be either 0, or 1, or 2. Those are the only possibilities, because only 2 players can use me. Furthermore, if I'm a resource in this congestion game, I have a twin, right? So if I'm R sub E S, I have a twin R sub E S bar. And actually, the same thing's true for both of us, right? So for both of us, only the players U and V can use us. And moreover, each player is going to use exactly one of us. Okay? If a player chooses its S strategy, it's going to use the S resource. If it chooses S bar strategy, it's going to use the S bar resource. Okay? So each of our individual loads is 0, 1, or 2. And actually, the sum of our loads is exactly 2. Okay? So if I'm RES, either I have 0, my twin has 2, I have 1, my twin has 1, or I have 2 and my twin has 0. Those are the only possibilities. Okay. So combined load of these 2 resources, RSE and its twin, RS bar E, is always 2. From the players U and V. Okay? Now, I haven't actually defined the cost functions yet, but at least now we know we don't even care about the cost functions with more than 2 players. Okay? So cost of a resource and its twin, it's going to be 0 if it's used by 1 player. And it's going to be equal to W sub E. What's W sub E? That's the weight of edge E in the given max cut instance. Okay? And we have to use those somewhere. Okay? So that's going to be the cost of a resource if it's used by the maximum number of players, namely 2. So again, if we sort of zoom in on a pair of resources, okay, corresponding to edge E, okay, resource and its twin, we have argued that their loads are either 2, 0, 1, 1, or 0, 2. Okay? If they're 1, 1, then both of these resources have 0 cost. Okay? If it's 2, 0, one of them has cost 0, the other has cost W sub E. Okay? All right, so that's the description of the congestion game. Any questions about that? That's a routing game.
That's a routing. So
Yeah.
let's see, what's the condition?
Instead of paths, they're just subsets,
Subsets what?
edges.
Okay. So like, okay, so they can pick between different
I basically give you a list. I say you're allowed to use resources 1, 3, and 5 as a group, or you can use 2, 4, and 7 as a group, or you can use 1, 8, and 10 as a group, and then there's some list like that.
Okay.
Yeah, and that's exactly what you're provided as input in the problem. Okay, good. So that's the construction. So we now have to do the correspondence, but this is the completion of the construction. Given a max cut instance, this is the corresponding congestion game. Okay. All right, so what's the correspondence? Well, what's hopefully very clear is that there's a bijection between the cuts in G and the strategy profiles in this congestion game. So by construction, there's one player corresponding to each vertex. Each player has a binary set of actions. So it can either choose S or choose S bar. And so those correspond exactly to, in a cut, for each vertex, you choose whether it's on the left side S or the right side S bar. Okay? So there's a correspondence between feasible solutions to the max cut instance and strategy profiles of the congestion game. Moreover, and this is the trickier point, let's think about the objective function values. Okay? And in some sense, it's the most natural connection you could hope for, but just the one thing that can be confusing is, remember, in max cut, we're maximizing, right? We want as many cut edges as possible. In the congestion game and the Rosenthal potential function, we're minimizing. Okay, so there has to be a minus sign somewhere in this connection. Okay? But subject to that, it's the sort of the most obvious transformation you could hope for. Okay? So for the cuts, what we care about is the cut value. I'm going to use the notation WSS bar. So WSS bar is just the total weight of edges that are cut by SS bar, okay, with exactly one endpoint in S and one endpoint in S bar. So if you consider a cut with some cut value, W of SS bar, I claim that maps to a strategy profile with Rosenthal potential equal to the sum of the edge weights. Okay, so this is just some fixed constant. This is just a million that doesn't depend on the strategy profile, minus the cut value over here. Okay? So the bigger the cut value, the smaller the Rosenthal potential. Okay? And that's what we want, because ultimately we want locally optimal solutions to correspond to locally optimal solutions. And, right, that's what we want. All right, so let's just see, why is this true? Okay, so given a cut, SS bar, and thinking about the corresponding strategy profile, where vertices corresponding to S choose their S strategy, vertices corresponding to S bar choose their S bar strategy, why is it that the Rosenthal potential is this? Well, the way I want you to think about this, think of this as the number of the weight of the uncut edges. Okay, so what do? I take the weight of all edges, and I subtract the edges that are cut. So this is weight of the uncut edges. Well, now remember what we said. We said consider the twin resources corresponding to an edge. The loads are either 0, 2, 1, 1, or 2, 0. If they're 1, 1, that corresponds to a cut edge. Right? So that corresponds to one player picking S and one player picking S bar. And in a cut edge, when both resources have load 1, both the resource costs are 0. So there's 0 contribution to the Rosenthal potential. Okay, so again, that means cut edges contribute nothing to the Rosenthal potential. It's fact 1. How about uncut edges? Okay, so that means either both vertices are on the S side or both vertices are on the S bar side. That means one of these resources is going to have cost 0, but the other will have cost W sub E, okay, with the two players. And so that the contribution to the Rosenthal potential of that resource with load 2, well, first you evaluate it with load 1, but with load 1 it's 0, and then with load 2 it's going to be W sub E. Okay? So cut edges contribute nothing to the Rosenthal potential. Uncut edges contribute the weight of that edge to the Rosenthal potential. So that's where we get this. Okay? So this bijection between cuts and strategy profiles basically just flips the objective function value. Maximizing the cut value corresponds to minimizing the potential function value. If you think about it, that means that locally optimal solutions on the left, so local maxima on the left, correspond to local minima on the right. Okay? So, guess I can't get away with that. So local opt of the original max cut instance correspond to pure Nash equilibria of the constructed game. And this means we're done. Okay. Why is it done? Well, to prove that the problem we care about was PLS-complete, all we needed was a reduction from max cut, and I've shown you the two algorithms. Right, so algorithm A takes this graph, constructs this congestion game. The second polynomial time algorithm needs to map locally optimal solutions of the target problem, meaning Nash equilibria, back to locally optimal solutions of the original problem, but there's an immediate correspondence. So you find me a Nash equilibrium, I'll just read off the corresponding cut. That's a locally maximum cut. Okay? So that's the reduction from max cut to pure Nash equilibria. All right, so questions about the reduction? So this also gives you a concrete sense of how it is that lower bounds on the running time of local search just sort of carry through the kind of reductions you see between local search problems. So I asked you to take on faith that for every PLS-complete problem, including max cut, I asked you to take on faith that for every PLS-complete problem, including max cut, local search takes exponential number of iterations in the worst case. And what we've seen here is in our reduction, we have just a bijective correspondence between trajectories of local search in the two different problems. So for every trajectory of local search of best response dynamics looking for a pure equilibrium, there's a corresponding trajectory looking for a locally optimal solution with the max cut instance. Since that is bounded below exponentially, so is best response dynamics looking for a potential, looking for a pure Nash equilibrium. Okay. So this reduction shows, again, piggybacking on the fact that max cut takes exponential time by local search, best response dynamics takes exponential time in the worst case. Okay. So any questions about that? So we should have a little bit more appreciation at this point for the result of Chen and Sinclair. So they did make a couple of assumptions in their theorem, but now we're starting to understand the sense in which they're necessary. Right? So they only focused on symmetric congestion games where all players have the same strategy set, but they really did show that best response dynamics, at least this 1 plus epsilon version of it, converges in polynomial time. And we now see that for lots of problems of this form, that's impossible. It just can't be done. Okay, so I'll see you on Wednesday, and we'll talk about PPAD and mixed Nash equilibria.